What do electric cars, wind turbines, and smartphones all have in common? They're all held back by weak magnets. The strongest magnets currently used around the world are made from rare earth elements, but they've already reached their limit. That limitation has slowed down progress in many industries. But according to reports, one company may have found a new way forward. Instead of improving rare earth magnets, they're using a totally different method to create magnets with much higher strength than ever before. If true, this breakthrough could completely change how devices are built and powered. The magnet wall that stopped progress. Picture this. Engineers have been hitting the same wall for decades, and most people don't even know it exists. Every motor that spins, every generator that makes power, every speaker that plays music depends on magnets. These magnets have a hidden weakness that limits everything. The problem is so big that it affects almost every electronic device people use daily. Here's what everyone needs to know about rare earth magnets. They're the strongest magnets available right now. Companies use them in electric car motors, wind turbines, computer hard drives, and smartphone speakers. But here's the shocking reality. These supposedly super strong magnets are actually incredibly weak compared to what physics says should be possible. Think of it like having a sports car that can only go 30 miles per hour when it should be able to hit 200. This weakness forces engineers to make devices bigger, heavier, and less efficient than they want. Take electric car motors as a simple example. The motor in a typical electric car weighs about 200 pounds. Most of that weight comes from the magnets and the extra metal needed to work around their limitations. The magnets just aren't strong enough to create the power engineers need in a smaller package. Wind turbines show the same problem on a much bigger scale. Those giant turbines have to be so big partly because the magnets in their generators aren't as strong as they should be. Engineers have to build huge structures to capture enough wind energy to make up for the magnetic weakness. The turbines could generate the same power in a much smaller size if the magnets were stronger. Here's how this limitation affects people's daily lives. Smartphone batteries drain faster because weak magnets make speakers, and vibration motors work harder than necessary. Laptop fans run more often because weak magnets in the cooling fans can't move air as efficiently. Electric tools need bigger batteries because weak magnets in their motors waste energy. The magnet problem touches almost everything with moving parts. The magnet industry has been stuck using the same basic materials for years with tiny improvements. Companies have spent decades trying to squeeze just a little more strength out of rare earth elements like neodymium. They've made small gains here and there, but the improvements have been incredibly slow. Simply put, the industry hit a wall and couldn't figure out how to break through. What makes this situation really frustrating is that the materials themselves aren't the main problem. Rare earth elements have plenty of magnetic potential. The issue is with how they're organized inside the magnet during manufacturing. Think of it like having a box of super strong workers, but they're all pushing in different directions instead of working together. Traditional magnet manufacturing creates what scientists call random domain alignment. Picture thousands of tiny magnetic regions inside each magnet, each pointing in a different direction like scattered compass needles. These regions fight against each other and cancel out much of their potential power. Most of the magnetic strength gets wasted before it can do any useful work. Scientists have known about this domain alignment problem for years. They understood that if they could line up more of these tiny magnetic regions in the same direction, the magnet would become much stronger. But they couldn't figure out how to control this alignment during mass production. Every method they tried was either too expensive or didn't work reliably at scale. The fundamental problem has been something called magnetic domain density. Most people have never heard this term before, but it's the key to understanding why current magnets are so limited. Higher domain density means more magnetic regions pointing in the same direction, which creates stronger magnetic force. Lower density means wasted potential and weaker performance. According to reports, one company claims they've found a way around this decades-old barrier. They've allegedly developed a completely different manufacturing process that creates ultra-high magnetic domain density. If this breakthrough actually works as claimed, it could solve the magnet wall that's been holding back entire industries for so long. The secret science of magnetic domains. Here's something most people don't know. Magnets aren't actually solid blocks of magnetic force. They're made up of millions of tiny regions called domains. Each domain acts like a microscopic compass needle, pointing in its own direction. Think of it like a massive crowd where every person is facing a different way. When all these tiny magnetic regions point in different directions, they fight against each other instead of working together. In most magnets that companies make today, these domains are scattered randomly throughout the material. Picture a parking lot full of cars facing every possible direction. Some point north, others point south, east, west, and everywhere in between. When these magnetic domains point in different directions, they cancel out much of their potential power. The magnet becomes much weaker than it could be if all the domains were lined up properly. Here's a simple way to understand this problem. Imagine a crowd of people trying to push a car. If everyone pushes in the same direction, the car moves easily. But if half the people push forward while the other half push backward and some push sideways, the car barely moves at all. That's exactly what happens inside most magnets. The domains are pushing against each other instead of working together to create maximum magnetic force. Traditional magnet manufacturing methods create this random domain scatter by accident. When companies melt down rare earth materials and cool them into magnet shapes, the cooling process creates domains that point in random directions. There's no control over how these tiny magnetic regions align themselves. The end result is a magnet that uses only a small fraction of its potential strength. Scientists have understood this domain alignment problem for decades. They knew that if someone could line up more domains in the same direction, the magnet would become dramatically stronger. Think of it like organizing that scattered crowd of people so they all push the car in the same direction. The force would multiply instantly. But knowing about the problem and solving it are completely different challenges. Previous attempts to control domain alignment during production have failed for several reasons. Some methods worked in laboratory settings but couldn't be scaled up to mass production. Others were so expensive that the resulting magnets would cost too much for practical use. Some techniques could align domains in small samples, but couldn't maintain that alignment in larger magnets that companies actually need. The manufacturing challenge comes down to controlling what happens at the microscopic level during production. Companies need to influence millions of tiny domains simultaneously while the magnet material is being formed. Traditional methods like heating, cooling, and applying magnetic fields during production only create partial alignment at best. Most domains still end up pointing in random directions. What makes this particularly frustrating is that the potential for stronger magnets has always existed. The rare earth materials themselves have plenty of magnetic capability. The problem isn't with the raw materials, but with how they're organized during manufacturing. It's like having all the ingredients for a perfect recipe, but not knowing the right way to combine them. According to reports, Niron Magnetics allegedly discovered a way to create ultra-high magnetic domain density using a completely different manufacturing process. They reportedly developed a method that lines up far more domains in the same direction than traditional techniques. Instead of letting domains form randomly during cooling, their process apparently controls domain alignment from the very beginning of magnet creation. This breakthrough approach allegedly involves manipulating the crystal structure of the magnetic material at the atomic level. The process reportedly creates conditions where domains naturally align in the same direction instead of scattering randomly. If this technique actually works as claimed, it could solve the domain alignment problem that has limited magnet strength for so long. What this breakthrough could mean for actual device performance has industry experts talking. Magnets with properly aligned domains could potentially deliver the kind of strength improvements that would make electric car motors much smaller and wind turbines far more efficient. The question now is whether this domain alignment technology can prove itself in real-world applications. The 10x performance promise. What if someone claimed they could create magnets 10 times stronger than the ones used today? Most people would call that impossible. But according to sources, that's exactly what Niron Magnetics claims they've achieved. The company reportedly developed magnets that can generate magnetic fields up to 10 times stronger than current rare earth magnets. This sounds like science fiction, but the technology allegedly uses a completely different approach to magnet manufacturing. Industry experts are reportedly skeptical about these dramatic performance claims. Magnetic technology improvements usually happen in tiny steps over many years. When someone claims a 10-fold improvement, experienced engineers naturally question whether it's too good to be true. The magnet industry has seen plenty of breakthrough promises that didn't pan out in real-world testing. Companies have learned to be careful about accepting bold performance claims without thorough verification. Here's what 10 times stronger actually means in practical terms. Electric car motors that currently weigh 200 pounds could potentially shrink down to 20 pounds while delivering the same power. Think of it like having a smartphone battery that's 10 times more powerful but the same size. Wind turbines could generate much more electricity from the same amount of wind. Solar panel tracking systems could move more precisely while using less energy. This level of improvement could make devices lighter, cheaper, and more efficient than anyone thought possible. Laptop computers could become incredibly thin because cooling fans would need much smaller motors. Power tools could run longer on smaller batteries because the motors would waste less energy. Electric bicycles could climb steeper hills while weighing much less than current models. According to reports, Niron's approach focuses on creating much higher magnetic domain density than traditional methods. The company allegedly uses a special manufacturing process that lines up more magnetic domains in the same direction. This reportedly creates stronger magnetic fields without needing more raw materials. The process apparently works with common materials rather than expensive rare earth elements. Here's the question everyone should be asking. If this technology works as claimed, why isn't it everywhere already? The answer involves the complex challenges of scaling new magnet technology. Moving from laboratory samples to mass production takes years of development and testing. Companies need to prove that new magnets work reliably in real devices before manufacturers will adopt them. The magnet industry is reportedly very conservative because failure in motors and generators can be catastrophic. A weak magnet in a wind turbine could cause expensive equipment damage. A magnet that loses strength in an electric car motor could strand drivers on highways. Companies test new magnet technology for months or years before trusting it in critical applications. Building manufacturing facilities for new magnet technology takes enormous investment. Companies need specialized equipment and trained workers to produce magnets with ultra-high domain density. The initial costs can reach millions of dollars before the first commercial magnet gets made. Many promising technologies fail during this scaling phase because the manufacturing proves too difficult or expensive. The timeline for proving performance claims adds another layer of complexity. Independent testing labs need time to verify that new magnets actually deliver the promised strength improvements. Real-world applications must demonstrate that the magnets maintain their performance over months and years of use. Motors and generators need extensive testing to prove they work reliably with the new magnetic technology. According to sources, several testing organizations are reportedly evaluating Niron's magnet technology. These independent assessments will determine whether the 10-fold performance improvement actually holds up under scientific scrutiny. The results of this testing could validate or debunk the company's bold claims about magnetic field strength. What this could mean for entire industries depends on whether the technology proves legitimate and scalable. If the performance claims check out, the impact could transform how people generate and use energy. Electric vehicles could become much more practical with lighter, more powerful motors. Wind and solar power could become more efficient and cost-effective. The potential applications seem almost endless if the science actually works as promised. The bottom line: Niron claims a large step change in magnet strength, and independent testing is reportedly underway. If those claims are proven and the process can scale, the impact on motors and generators could be significant, but that's a big if. The question isn't whether better magnets would revolutionize technology. Everyone knows stronger magnets would make motors smaller and generators more efficient. The real question is whether companies like Niron can actually deliver on their promises at a scale that matters for regular people. Stronger permanent magnets could improve efficiency and shrink hardware. They do not, on their own, overturn the laws of physics or create free energy. If you want updates on the tests or have thoughts on where this tech could matter most, leave a comment and subscribe. We'll follow independent test results closely.